Hi, I am Neil. Thank you for joining in today to NCS Forum. I welcome you to what is going to be the start of a wonderful journey of exploration. And what is this exploration? This exploration is about answering the three fundamental questions that we have always had in our minds. According to me, the three questions are: who am I? Is there a God? And if so, who he or she is? And what is out there in the universe? Before we begin, a huge shout out and a very big thank you to my mentor, Dr. Anil Jain. He has guided me towards this discovery and journey of quantum computing, AI, machine learning. Thanks to you, Dr. Jain, that I'm having a great time in understanding this seemingly infinite world of quantum computing and the endless infinite possibilities that come along with it. Thank you. Up to yesterday, this journey of exploration was a near impossible task to achieve. But no more. Let's deep dive into it. To understand quantum computing, we need to understand the history of computers. The analog computer, the digital computer, the supercomputer, and finally, the quantum computers. Let's have a look at a video by Professor Dr. Michio Kaku, physicist, quantum physicist and professor, City of University in New York. Let's have a look at what he has to say about quantum computers.
We all know that digital computers change virtually every aspect of our life. Well, the arrival of quantum computers could be even more historic than that. Computers have gone through three basic stages. Stage one was the analog computer. So 2,000 years ago, there was a shipwreck. And in the boat that sank was a device, and when you brushed away the dirt and debris, you began to realize that it was a machine of incredible complexity. It was, in fact, the world's first analog computer, and it was designed to map the motion of the moon, the sun, and the planets to simulate the universe. But as we primitive peoples became more prosperous, we had to count things. Analog computers could be based on sticks, bones, whatever it took to count. So this went on for thousands of years until finally we reached the work of Charles Babbage. He creates the ultimate analog computer with hundreds of gears and levers and pulleys. Then World War II comes along. Babbage's machine is simply too primitive to break the German code, so the job was given to mathematicians like Alan Turing. Alan Turing was the one who codified a lot of the laws of computation into what is called a Turing machine, and of course is digital. Now, the digital revolution is based on transistors. It operates on zeros and ones, at the speed of electricity. Every digital computer is a Turing machine. The next step beyond digital computers is the quantum era. Richard Feynman was one of the founders of quantum electrodynamics, but also a visionary. And he asked himself a simple question: how small can you make a transistor? And he realized that the ultimate transistor is an atom. One atom that could control the flow of electricity, not just on or off, but everything in between. We have to go to quantum computers, computers that compute on atoms rather than on transistors.
So how does quantum computers work? Again, Dr. Michio Kaku has explained this in a very simple but in a very illustrative manner. Today in this video, we will only look at the basics of how quantum computers work, just the introduction part. And in another separate video, I will detail out how quantum bits or qubits work differently than the current binary bits or bits which is there in the supercomputers and digital computers. Let's have a look at what Dr. Michio Kaku has to say about how quantum computers work.
Transistors are based on zeros and one. Zeros and one. Reality is not. Reality is based on electrons and particles. And these particles in turn act like waves. So you have to have a new set of mathematics to discuss the waves. And that's where quantum computers come in. They're based on electrons. And these electrons, how come they have so much computational power? Because they can be in two places at the same time. That's what gives quantum computers their power. They compute on not just one universe, but an infinite number of parallel universes. So how much faster is a quantum computer over a digital computer? In principle, infinitely faster. And so we're talking about exceeding the power of ordinary digital computers. That's called quantum supremacy. We passed that several years ago. But we want a machine that could exceed the power of any digital computer. We're not there yet, but we're very close to it.
Up to a couple of years back, quantum computing had not reached that stage where one could say, it has evolved to a level where now it can be mass produced and used for the purposes that it were meant to be used. But now, in the last 1 year or less than that, many companies that were in the race or that started the race as far as 30 years back have now almost reached their goal, and Google has reached that goal or the end line, the current first milestone end line, faster than the others.
The question is, who's involved in this race to perfect quantum computers? And the answer is everyone. All the big players are.
So what has Google done that has got the world so excited? They have finally cracked the errors that were getting generated due to incoherence in quantum computing by reducing that error to a level that is below the maximum threshold of errors that is permissible. This chip is called Willow. And here's what Google has to say in the launch video of Willow.
The systems behind our universe are quantum mechanical. They shift and change with the problems they're tasked to solve, exploring a vast array of options all at once. And like nature, quantum computing is responsive to the environments it works within, leading us to new breakthroughs for tomorrow's most challenging problems. Introducing our latest quantum computing chip, developed to learn and evolve like the natural world around us. Willow, from Google Quantum AI.
Hi, I'm Julian Kelly, Director of Hardware at Google Quantum AI. And today, on behalf of our amazing team, I'm proud to announce Willow. Willow is Google's newest and most powerful superconducting quantum computing chip, and the next step in our path towards building large-scale quantum computers and exploring their applications. I've been fascinated with quantum computing since I first experimented with qubits in 2008. And since coming to Google in 2015, it has been a dream to make our mission a reality, building quantum computers for otherwise unsolvable problems. We launched our first chip, Foxtail, in 2017, followed by Bristlecone in 2018, and Sycamore in 2019, which powered our milestone 1, the first quantum computer to surpass the best classical supercomputer on a computational task random circuit sampling. Over the years with Sycamore, we have been able to squeeze a remarkable amount of performance from our hardware, including achieving a scalable logical qubit in our milestone 2. But we've ultimately been limited by quantum coherence times, the length of time qubits maintain their intended state. With Willow, we've made a huge step forward. We've increased quantum coherence times by a factor of 5, going from 20 microseconds in Sycamore to 100 microseconds in Willow. And we've accomplished this all without sacrificing any of the features that made our systems so successful. This advancement was enabled by our new dedicated superconducting quantum chip fabrication facility in Santa Barbara, one of only a few in the world. And we're seeing exciting developments coming from Willow, which has already surpassed Sycamore's breakthrough demonstrations. Our logical qubits now operate below the critical quantum error correction threshold, a long sought-after goal for the quantum computing field since the theory was discovered in the 90s. And we've achieved it for the first time with Willow. Errors are exponentially suppressed in our logical qubits, as error rates are halved each time we add physical qubits in scale from distance 3 to 5 to 7 surface codes. Additionally, our logical qubit lifetimes are now much longer than all of the lifetimes of the physical qubits that compose them. This means that even as we make our quantum chips larger and more complex by adding more qubits, we can use quantum error correction to actually improve their accuracy. We've pitted Willow against one of the world's most powerful supercomputers with the random circuit sampling benchmark. The results are pretty surprising. By our best estimates, a calculation that takes Willow under 5 minutes would take the fastest supercomputer 10 to the 25 years. That's a 1 with 25 zeros following it, or a timescale way longer than the age of the universe. This result highlights the exponentially growing gap between classical and quantum computation for certain applications. Let's talk about the hardware approach we've pioneered at Google Quantum AI that makes these things possible. Our tunable qubits and couplers enable super fast gates and operations to achieve low error rates, reconfigurability to optimize hardware in situ and run multiple applications, and high connectivity to efficiently express algorithms. We leverage this tunability to enable reproducible high performance across the device. Let me explain. A challenge in superconducting qubits is that not all of them are created equal. Some are outliers with uncharacteristically high errors. But here's where our tunable qubits really shine. We're able to fix these outlier qubits by reconfiguring them to perform in line with the rest of the device. And we can go one step further by having our researchers use tunability to continuously develop new calibration strategies that push errors down across all qubits with software. Let's quantify this and nerd out for a minute on quantum computer tech specs. We have number of qubits. Connectivity is the average number of interactions each qubit can perform with its neighbors. We quantify error probabilities for running simultaneous operations. Single qubit gates, 2 qubit gates, and measurement. Coherence time measures how long each qubit can retain its information. Measurement rate is how many computations we can run per second. And application performance is a full system benchmark. Willow hits a sweet spot across the full list. It has a large number of qubits with high connectivity and can run diverse applications. We measure low mean error rates across all operations with multiple native 2 qubit gates. We have greatly increased T1 times. We have very high measurement rates, and Willow is below the error correction threshold and performs random circuit sampling far beyond what is possible with classical computers. Looking to the future with Willow, we continue our journey towards building large-scale and useful error-corrected quantum computers that will push the boundaries of science and the exploration of nature. With future commercially useful applications in areas like pharmaceuticals, batteries, and fusion power, we are excited to solve the otherwise unsolvable problems of tomorrow.
So that's Google's quantum computing chip, Willow. Google has done its work in manufacturing a quantum computing chip that is almost error-free and coherent. But to make this chip work, it needs a hardware, a base, or a platform on which this chip can be placed and supported with the data bandwidth speed hardware, the cloud computing processes and the cloud computing speed, the temperature and the environment where such a machine can be kept. Without this, Willow on a standalone basis cannot do anything, right? So let's see, exciting times ahead. The future is bright as far as quantum computing is concerned. We have taken the first step towards a world of artificial reality, augmented reality, and a much better world, hopefully, with the use of quantum computers. However, with great power comes great responsibility. We have seen the movie Spider-Man, right? So quantum computing power is next to God. It surpasses the human mind. However, the raw data, the first seed raw data that is entered into the quantum computer is done by a human brain or a human mind. While the quantum computer is unlimited, infinite potential device, still it is the human brain or the human mind that decides the limit of that device, at least to start with, because a quantum computer is supposed to be a self-learning, self-evolving machine, thinking machine. We have all seen the latest series Dune Prophecy, where thinking machines took over the planet and afterwards they were defeated and banned from use. We have seen the movie Terminator. We know what can go wrong if we do not use this power responsibly and with a highest degree of integrity. So what can happen if we don't use this power responsibly? In the next chapter, we will see how qubits work as compared to bits or binary data, and we shall see the spheres or the fields where quantum computers can potentially impact our lives positively or negatively. Thank you for watching this video. Have a great day ahead, a great week ahead, and a great end to this financial year 2024 or calendar year 2024. Till then, take care. Bye. Cheers.